All right, so let's talk about collisions. And the definition of a collision, it's an event in which two particles come close to each other and interact by means of some force, okay? So that could be just the normal force of two things hitting each other. If you have magnets, they could repel and bounce off of each other without actually contacting. If they're charged, they can also interact without actually contacting. And we know for that momentum is conserved in all situations where two particles or more particles interact, okay? There's two different types of interactions. There's direct, which involves physical contact, usually just a collision where these two things actually hit, and that's a normal force that's part of an action-reaction pair. And there's also indirect, which is a force interaction like gravity, either like a gravitational interaction or an electromagnetic interaction for the most part, okay? And remember, because the impulse on each object in all of these cases is going to be equal and opposite, we know that momentum is conserved. All right, so let's break these down into types. So an inelastic collision is when momentum is conserved and objects don't necessarily stick together. All right, a perfectly inelastic collision is when objects stick together and move as one object after the collision, okay? An elastic collision means that momentum and kinetic energy are conserved. So what that means is usually it means they're not touching. This is not the best example of this, but usually that means usually you get these from indirect contact, okay? So inelastic is just a standard one. Perfectly inelastic means there's some point where the objects stick together, and elastic means that you also conserve kinetic energy. Okay? Cool. Let's skip that. So let's talk about inelastic collisions. So remember, an inelastic collision is just any general collision where things don't stick and energy is not conserved. Okay? So the way it's set up is you use conservation momentum. That means initial momentum is equal to final momentum. Because we have two objects, you have the initial momentum of object 1 plus the initial momentum of object 2. So in this case, you would just say mass times velocity for each of these. And then your final situation is going to be the final momentum of object 1 plus final momentum of object 2. Remember, momentum is just mass times velocity. So this is the sort of standard look to these conservation and momentum problems, okay? The special cases are the perfectly inelastic collision. That one is easier just because at the end you only have one momentum. This also works in the opposite direction. If you have something that explodes, you could start with a momentum of 0 or a momentum of one single object, and then it becomes different pieces. All you have to do is flip this around and it's the same basic idea, okay? We'll talk about the elastic collision in a second, but we're going to try an example of a perfectly inelastic collision with a skateboard. So let me set that up. So we have a kid with a mass of 60 kilograms. He's skateboarding at a constant speed of 3 meters per second towards his dad. The dad throws the kid his backpack at a speed of 5 meters per second. We want to know the speed of the kid after he catches the backpack, okay? So let me draw this out. So essentially, we have an initial and final condition. Just that this way. So here's kid, skateboard, and he's going this way. 3 meters per second. So call this VK initial, and that's going to be 3 meters per second. He's going directly towards his dad, so we'll put dad over here. Dad's got a backpack. All right. The backpack, when it's thrown, is going to be, let me move this over. Moving at, we'll call this VB for backpack. so this is -5 meters per second because it's going in the opposite direction, okay? And then at some later time, oh boy, they got really big. At some later time, we've got the kid wearing the backpack. I'll make the backpack gray. And still moving in this direction with some speed, which is probably smaller. We'll call that V final, okay? So this is our start before, and this is our after. You could also call these initial and final, okay? The other thing we want to remember is the masses. So here, this is a mass of, let's call this big M, is 60 kilograms. The backpack has a mass of 10 kilograms. And here we have M plus M, which should be 70 kilograms. All right? So we want to start with conservation of momentum. That just looks like this. This is the equation that we write for that. So P initial is equal to P final. And remember, these are vectors, but all of these vectors are in the x direction. The only thing we have to keep track of are the negative signs, okay? So our initial momentum would be the momentum of the kid plus the momentum of the backpack. So the momentum of the kid is going to be mass of the kid, which is this big M, plus V kid initial, plus the mass of the backpack, and that's V backpack initial, okay? And then last, the last part, the after part, that's going to be the total mass, M plus M, times V final, okay? The only thing to really be thoughtful about here is that this is going to be a negative velocity, because you can see the negative right here. So when we plug that in, it's going to be a subtraction instead of an addition, okay? So we write this out, we solve for V final, and that ends up being mass V kid initial plus mass of the backpack, V backpack initial, over the total mass. So when we plug these in, we end up with 60 kilograms times 3 meters per second plus 10 kilograms times -5 meters per second divided by 60 plus 10, which is 70 kilograms. We're running out of space, so I'll make this a little smaller. And when we put all that together, that's going to give us a final speed. And before we even get to the final speed, do you expect it to be larger or smaller than 3 meters per second?
Smaller.
Smaller, right? 2 reasons. One, there's more mass, and 2, he's throwing the backpack really fast in the opposite direction, okay? There's some passive-aggressive dad things happening here. But yeah, so we're expecting it to be less than 3 meters per second, and it turns out it is 1.86 meters per second. Just a question, let's say he threw it even harder.
Go backwards.
Yeah, could he stop the kid or turn him around? Yeah. That would be kind of messed up. So at least he's not doing that. But yeah, the final velocity is this. So we've now done a conservation of momentum problem, and we could predict sort of how that was going to turn out. Any questions on this?
It's not that fast.
5 meters per second?
It says it's like 11 miles an hour.
Yeah.
Never mind, I thought it was a lot faster.
No, remember the way to estimate in miles per hour, approximately, it's like a really bad estimation, but it works for like getting the idea, is to double meters per second to get miles per hour. The higher speeds, that gets worse, but for like normal speeds, it works pretty well. All right, cool. So that's how we do a conservation momentum problem for inelastic collisions. Do we want to try another one of these? Do one like a more complicated one? We could also add energy back into this. No? Feeling good about that? All right.
Add energy back in.
Add energy. You want to do that?
Well, no, but that's why I want to do it.
Okay, we can try one of those. So here we're gonna have mini Tarzan. He's on top of a 200-meter high cliff. He only weighs 2 kilograms. That's why he's mini. How much does so remember the kid weighed 60 kilograms. This is a very mini Tarzan. So this problem, just the reason I'm telling you that is it's gonna have some very unrealistic numbers in it, but it's just for practice. So we're at the top of a 200-meter cliff. We're holding on to a 200-meter long vine. We have Mini Jane at the bottom of the cliff, and he's gonna swing down and pick up Mini Jane. And then we wanna know how fast he's going when he reaches Mini Jane, and then what's the highest tree branch they can reach on the way up. So this has got 3 parts to it, okay? There is the first part, which is an energy conservation part, right? And the energy conservation part is the part where Tarzan swings from the cliff down to the ground, okay? Why is that energy conservation?
Because it's turning potential energy into kinetic energy.
Yeah, we're turning potential energy into kinetic energy. There's no friction. We're gonna ignore any drag, and there's no collisions, okay? Because remember, energy conservation requires that we don't have any dissipative forces, meaning friction and collisions for the most part.
Because it's not an inelastic collision when he picks up.
So it's an inelastic collision when he picks her up, because that is 2 things becoming one thing from a physics perspective, okay? So he has to grab onto another object. Remember, what's her initial momentum though?
0.
0, yeah. So he's gonna grab onto another object, that's just gonna change the mass. That's an perfectly inelastic collision. And then once they're one object, right, they swing back up and they're gonna get to another height. That's another energy conservation problem, because from the time he picks her up to the time they get up to the next height, that's an energy conservation problem because there's no more collisions happening and there's no more friction, okay? So 3 parts to this problem. I'm gonna start by drawing it out. And so it's gonna be a fun drawing. Okay, so let's start with Tarzan on the cliff. Oops. Oh boy, that's not good. Okay, so he's up here. Here's a rope. Not quite there. Maybe there. And then at some point, he's swinging. And Jane is here. I guess she can have a dress or something. Okay. There, that's Jane. And then at this point, there's together. This is not a good drawing, but you get the idea. And then later they end up at some point. And do we think they're gonna go as high over here? No. I'm just gonna duplicate that because I don't want to redraw it. There we go. So that it's not the best. And so I'm gonna color code this just so we can keep track of it. So we'll start with I guess pink. So this is this situation. Then we'll go purple. That's part 2. We'll do blue over here. And then green. Okay, so essentially we're breaking down, so there's energy conservation. We'll call this from here to here. This is step 1. From here to here, this will be 2, and from here to here, this will be 3. Okay, this would be energy. This will be momentum, and this will be energy again. Okay, so part 1 is going to be energy conservation. This is a 200-meter height. So what do we use for energy conservation? What's the initial energy?
There's potential.
Potential, right? Gravitational potential energy. So let's call this height, I'm gonna call it H. And then we'll call this height little h, because I really don't like subscripts because they're annoying and they're probably hard for you to see. So we're gonna start with energy conservation. So we'll also call Tarzan big M and Jane little m, okay? So we'll start with mass of Tarzan, GH, is gonna be equal to 1/2 mass of Tarzan times velocity, let's say initial squared, and that's gonna be this velocity. So he has a velocity here, that would be v initial, and then there's gonna be a different velocity here, which we'll call v1 for the sake of it. So we can cancel out the m's, and we get our initial velocity, which is going to be the square root of 2gh. Okay, and we can actually figure that out. So the square root of 2gh, this is what happens before the collision, is going at the breakneck speed of 62.6 meters per second. Okay, so like I said, unrealistic speeds, okay? So that's from this stage, so I'm gonna just color code this. So it's from the pink to the purple, okay? All right, let me move this over so we have some space. Oh no. I've ruined everything. Okay. Cool. All right, step 2. What happens during step 2? That's from here to here, so from purple to blue. What are we conserving here? I'll put it down here.
Momentum.
Yeah, I'm gonna put it back up there. So momentum conserved. All right, and that's going to be from purple to blue. Okay, so that means we want to use conservation momentum, which means P initial is equal to P final. Okay, our initial momentum is, we have 2 objects. So we have Tarzan's momentum and Jane's momentum. So what's Tarzan's momentum?
62.6.
Yeah, so 62.6 times his mass, right? Plus, what's Jane's momentum?
0.
0. Why is it 0?
She's
She's not moving, so it doesn't matter what her mass is. And then finally, it's gonna be m plus m. We'll call that v1. Okay, so v1 is gonna be equal to mass times the initial velocity divided by the total mass. So that's going to be 2 kilograms times 62.6 meters per second divided by 3 kilograms. Okay, so are we expecting this speed to be bigger or smaller than before? Smaller, because even though she's not moving, she's added extra mass to the system. So they're gonna be moving a little bit slower, and they're going down to the slow speed of 41 meters per second, so just 80 miles per hour. Okay, very safe. Essentially, these tiny people are dead, so hopefully they're like ants and they have super strength and durability. Okay, so here's our initial speed, which it asked for. Then this is our speed after the collision, which we haven't been asked for. And then last but not least, we have another energy conservation problem, where we go from blue to green. Okay. What do we start with? What kind of energy?
potential.
Yeah, so we have kinetic, right?
Well, let me start with
Speed.
potential.
Oh, no, we're just from here to here though. So here we're moving, there's a speed, so we start with kinetic energy. So that's going to be 1/2 m plus m v1 squared. I ran out of space already. Okay, and then our final should be m plus m g lowercase h. All right, and here we're trying to solve for h. Once again, the masses cancel because we're not losing any mass in between these two things. There's mass on both sides. So h is going to end up being v1 squared over 2g. So that's going to be 41.7 meters per second squared over 2 times 9.8 meters per second squared. And that's going to give us a height that we're assuming is going to be smaller than 200 meters, and that's 88.7 meters. So that is our final height. And that's this. Okay. So when we're doing these problems, we want to break down where energy is conserved and where momentum is conserved, and then just solve the problem in pieces. All right. Not least, we will talk about elastic collisions, which are sometimes in some textbooks called perfectly elastic collisions. But remember, the exciting thing about elastic collisions is that they conserve both momentum and kinetic energy. Okay, and this usually happens because we do not have any direct contact between our two objects. So we have momentum conserved. We already have worked out what that looks like. But in this case, energy is also conserved, which means that kinetic energy initial is equal to kinetic energy final. Now, there's a lot of math that happens here. Like, this is to show how we get these equations I'm going to show you next. There's like an algebraic mess. But essentially, kinetic energy initial is 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared is equal to 1/2 m1 v1 final squared plus 1, et cetera, et cetera. So you end up with two equations that have 4 terms, and then you do a lot of algebra. I'm not going to go through all of that algebra, but if you really want to do it for funsies on your own, you're more than welcome to. It's definitely sort of half spelled out in the book, but the answers end up looking like this, okay? So if you want to find your two final velocities, they look like this. What's neat about this, well, what's not neat about this is the horrible amount of equation and algebra that you have to keep track of. What's really cool about it is you can solve a lot more problems because you have now two different concepts you can apply to give you information about what's going on. So just to test that this makes sense, we'll try some extreme cases to see if it works. So if something big hits something small, what do you expect to happen?
Small thing get crushed.
The small thing has ends up with a lot more of the energy after, right? If things are about equal, you kind of expect things so if you have two things that are the same mass and they hit each other, if one of them is moving and one of them's not, you'll expect it to make the other one move. Okay, kind of like a what's that, Newton's cradle thing? I think we have one in the back. But if you're thinking something stopped, that means if M2 is at rest, okay, and M1 equals M2, you're gonna expect to get a situation that looks like this. So can we test this on these equations? All right, so what does M2 at rest mean? What does that do to this equation? Yeah, V2 initial goes away, so this term goes away, and you end up with M1 minus M2, right? What does that give us if they're equal? 0. So this is 0 plus 0, so this whole thing is 0. We said V1 final should be 0, that's what we see. Okay, over here, this term goes away, right? In this case, we have V1 initial, which is not 0, so that means the total thing ends up being, so this is 2m1. If m1 and m2 are equal, what is this? 2m1, so those cancel. You end up saying that your final velocity of V2 should be the same as your velocity V1. Okay, so it works in that case. You can also say if M2 is at rest and 1's really big, you can try this yourself, right? In this case, you say that this is approximately equal to the negative version of this, and V2 final is approximately 0. But essentially, if something's really big and you hit it, you bounce off of it. okay? And if you plug those values into this equation, it still works. So this is just sort of we don't have to do a bunch of algebra proof that this equation makes sense, okay? So these equations are something you can derive, you don't have to derive, you can write them down and just use them in a situation where you have an elastic collision, okay? Inelastic collisions are much nicer, all right? So let's try a problem. This is similar to the Tarzan problem in that it includes both conservation of energy and conservation of momentum. I'm gonna give you guys about 3 minutes to work on this, and then we'll talk about it after. All right, do we feel like we want more time with this, or do we wanna?
I don't wanna do it.
No? Cool. You guys are highly motivated today. I'm just glad everybody's eyes are open. Okay. I used to for some reason my entire life I've gotten sleepy after lunch. I mean, I think that's a fairly normal thing. It probably means I should just move to Spain and give up. But whenever I'd schedule an afternoon class, I would sit in the front so I wouldn't fall asleep. But then it's just extra embarrassing if you fall asleep in front of there's a 200-person lecture and you're passed out in the front row. But so then I started carrying these mints that had caffeine in them, right? It was each mint was a third of a Diet Coke or something. That was the level of caffeine. So I was I could just anytime I get sleepy, I'll just eat a mint, and I'd eat 1 or 2 or 3 mints and basically drink a whole can of Coke. I didn't drink coffee in because I was stupid and I didn't know it would be helpful. Anyway, caffeine's not bad for you. It's the sugar. So the best part was, though, this was back in the olden days when people studied in libraries. Do people still study in libraries? I don't know. But the library at Berkeley, it was this crazy, the main stacks where all the books are is underground. You go into the library, it's all pretty, and then you just go down 2 or 3 stories. And at the time, if you went down I think it went down 5 stories underground, and all the books are underground. And it was really quiet and nice to study. If you talked or made any noise, people would give you a death stare, and a librarian would come yell at you, which was great if you wanted to study. And if you wanted a study room, you had to book one, right? So I'm down there because at the time there was no Wi-Fi down there, so it was harder to get distracted because I couldn't use the internet. And so I'm down there studying, but I'm starving, but I want to finish as organic chemistry, which is part of the reason I didn't become a biologist, is I did not like that class. So I'm hungry, but the only thing in my bag is this is a box of mints. So I'm just absently eating these mints and drawing stupid chemical structures. And then 20 minutes later, I'm I feel really terrible, so awake that it hurts, and really jittery and anxious. And I was I just ate a whole box of caffeinated mints, and I need help. So I had to leave and give up studying for the day. But anyway, I don't know why I'm telling this story. So let's talk about this elastic collision. So what's going on here? Essentially, this guy. So this block, it's still a 3-part problem. You start with conservation of energy. This block comes down here. It collides with this block, okay? Yeah. And then block B goes this way and block A goes back up, okay? And this is an elastic collision. When you think of elastic collisions, it's supposed to be energy conserved, but a good estimation of an elastic collision, even though it's not perfectly elastic, is a pool ball collision where things bounce off of each other, okay? So you're just thinking about things bouncing off of each other. So the first part is just a conservation of energy problem. So that's from here, so this shot to, I'm gonna try to draw a crappy box A. So at this point, right, there's a box A, and it's got a speed, we'll call V. VA final, okay? And so VA initial, because it's before the collision. So VA initial, okay? So that's going to be, in the terms of the next thing we're doing, that's going to be V1 initial. So that would be these speeds, okay? What's your initial, we're kind of skipping ahead, we'll get to the energy conservation part, but I just want to focus on the momentum conservation part because that's the new part of this. So what's V2 initial? What's the initial speed of B?
Zero.
Zero. So all of these guys, anytime you see V2 initial, this is 0 and this is 0. Okay? So now we've got a much simpler version of these equations and that's usually what happens in these situations is you're not going to end up using all of this equation. Okay? So just to start out with, for part 1, this is conservation of energy. And that's from here to here, okay? So we start out with, let's call this mass A, G, and H. I'm just gonna call H is equal to 8 meters, is equal to mass A, 1/2. So potential energy to kinetic energy, mass A, V, A, initial squared. All right, so then we just do this and we end up with B A initial is equal to square root of 2GH. So that's going to be square root of 2 times 9.8 meters per second squared times 8 meters. That means our initial speed is going to be, I've lost math I did already, 12.5 meters per second. Okay, so that's the initial speed. All right, the next part is what? It's the collision, right? So if the next part is our collision, what's conserved?
Momentum.
Yeah, so that would be from here, right? So this situation to then, you're gonna have B over here, and this one's gonna have B final, and then A is gonna be turning around. So let's say there's an A over here, and that's gonna be V A final. Okay, and just for clarity, let's say VA final, that's going to be the same as V1 final. Just anytime you see a 1, substitute it with an A. And then VB final, that's going to be the same as V2 final. Okay, so for this part, this is actually conservation of energy and momentum. So to be clear, if you want to, you don't have to use these formulas. You could actually do the momentum part. You could say, it would be, I'll write it out just for the sake of it. It would be MA VA initial plus 0 is equal to MA VA final plus MB VB final. You see, you can't really solve that, but then you could add the 1/2 MA VA initial squared is equal to 1/2 MA VA final squared plus 1/2 MB VB final squared. All right, you have two equations, you have two unknowns, which is your final velocities, and you'll end up, if you do them, with this. Okay, so even if you can't remember these formulas, you didn't write them down, you can still solve from here. But if you have this formula, it's much faster just because you have to do less algebra. So I'm gonna not use this, but just trust me, if you solve this, you'll get the same thing. It's just algebraically unpleasant, okay? So looking at this, we say, okay, look, we have V A final should be equal to M A minus M B. Okay, there we go. V A initial divided by M A plus M B. And all I've done is I've taken this formula and I noticed that since V, the initial speed of B is 0, I got rid of this term. And then I just changed all the 1s to A's and all the 2s to B's. So just plugging into that formula, okay? If you want to actually solve this, then you say MA minus MB, that's going to be 5 minus 10, so this is negative 5 kilograms times VA initial, which is I lost it. 2.5?
12.5.
12.5. Oh yes, we did it over there. Divided by 15 kilograms. So you'll notice this gives us a negative from the masses, which is good because we can see just from the way the collision works that it should turn around. So that means we'll end up with negative 4.17 meters per second. Okay, so that's going to be our VA final, and that's VA final. Let me just make this a little smaller so we have space. Okay, we can do the same thing for VB final. Okay, we just look at this equation over here and we see that we end up with 2 MA VA initial over MA plus MB. So that's going to be 2 times 5 kilograms times 12.5 meters per second divided by 15 kilograms. And that's going to give us a speed of 8.35 meters per second. And we can just color code that so you can see what that looks like. Okay. Any questions so far? I wish I knew how to use this thing better. Okay. So now we've started from a conservation of energy problem. We use that to get our initial speed for the collision. After the collision, we have these two speeds. So you have block B moving forward at 8.3 meters per second, and block A is going back up the ramp at 4.17 meters per second. The negative includes that it's turned around. So that gives us, the question's asking how fast is MB moving, so we already have that answer. And then we also want to know this last question, which is what is the maximum height to which the other mass goes? So in order to get the maximum height, what do we need to do? What's the height for which block? A. So we now have the speed for block A, so we just need to turn that into a height, so we use energy conservation again. So that just says mass A, so 1/2 mass A VA final squared is equal to mass A G, let's say lowercase h in this case. So the masses go away and we end up with h is equal to VA final squared divided by 2g. You can plug all that in. I'm not going to write the numbers just because we're out of space over here. But when you do that, first off, do you expect it to be higher or lower than 8 meters?
Lower.
Lower. Why? Do you have the same amount of energy you started with? No, what happened to that energy?
It's B.
Yeah, some of it got transferred to block B. Block B has a lot more mass, so this block A had to turn all the way around, so you expect it to be lower, and you end up with 0.89 meters. So it's gonna go not very high at all, okay? Okay, so when we're doing these problems, the first thing you want to look for is collisions, okay? If you have a collision, then you switch to to momentum conservation. If you have momentum conservation, the key thing is asking what kind of collision it is, okay? Is it inelastic? Do things stick together? Do things bounce off of each other? Then therefore it's elastic. Do you have any energy loss that you could account for, then it would be inelastic but not perfectly inelastic, okay? So there's 3 different options, and depending on which option you're using, you use slightly different formulas, okay? Now just remember, for all collisions, you can always conserve momentum. What you're really looking for is, can you also conserve energy in the collision? All right, and there should be hints. It should either say it's an elastic collision or no energy is lost during the collision, in which case you can use this formula, all right? The other thing you want to look for is, can you get the things you need for the collision from conservation of energy? Do you have a spring? Do you have a changing height that leads to a speed? Those sorts of things. So then you just break it down into the stages of the problem and make sure. I think the color coding helps a lot. And drawing pictures helps a lot. If this one's confusing to you, you could draw out all the multiple stages. I only didn't do that because there's not a lot of space here to do that, but that could also be a good thing. Like with the Tarzan problem, having each stage color-coded really helps visualize what's going on. So momentum is a vector, remember, and we haven't really addressed that because we've conveniently only talked about momentum that moves in one dimension, okay? So we've pretty much only dealt with momentum all in the x direction, but just for the sake of treating it as a vector, remember that the way the velocity breaks down, the way the momentum breaks down is the same direction. So your momentum vector points in the same direction as your velocity vector, okay? So anything you do in terms of velocity can be used, all the vector stuff we learned from the first couple chapters, that can still be used in this situation. So speaking, I don't know why I chose to do these with all, I think I just didn't want to write 30 kilograms, but anyway. Here we have a little fake toy car collision. So a toy Cadillac collides with a toy Volkswagen heading in different directions. The cars stick together, so what does that tell us about the problem? What kind of collision is this?
Perfectly inelastic.
A perfectly inelastic collision. So energy is not conserved, okay? We're not going to deal with energy at all in this problem. They stick together and they slide to a halt. They leave skid marks at a 35-degree angle in the northeast direction from the point of impact. We want to know how fast was the first car going, okay? So why don't we take a minute and look at this, and then I'll set it up, and then I'll give you a little bit of extra time to try to sort out the answer. But try to draw out the problem first. That's the easiest place to start, and then we'll go over it in a little. Okay, so let's at least draw this out first. We have a before and after situation. It's best to draw this from above. Remember, in case you're unfamiliar with compasses, this is north, right, south, and then west, east, okay? Just as a reminder of which way those directions go. And so I've seen some truly beautiful drawings of cars out there, and I appreciate your artistic efforts. That is a part of physics that I enjoy as well, is drawing pictures, although not cars. For some reason I hate drawing cars. So we have a Cadillac heading north. I'm going to draw it as a dot. I'm going to call it C for Cadillac. So here's our Cadillac heading north, right? And I'll draw that with a green arrow. It's heading north at a speed of 3 meters per second. And then we have a Volkswagen heading east at a speed of, I lost it. Oh, we don't know. V. We'll call it B. Or I don't know what to call this. Volkswagen? Okay. It's too many subscripts, but whatever. Okay, and then after these two things collide, you end up with basically these two things stuck together, and they're going to have a speed here, which we'll call V final, and that's going to have an angle of 35 degrees from the collision point, okay? And so that this angle is north of east, so north of east, all right? Any questions about this? Okay, so this is our, this is our before. Oh, weird. Why would it make, I drew such a bad triangle that it wow, it did a rectangle that didn't believe me. Okay, This is before, and then this is our after. Okay. So the key thing here is that we are using vectors, so everything has to be in the x or y direction, right? So we're just gonna wanna break this into oh, that's a terrible color. Can anybody see that color? Is it okay for you guys?
Yeah.
Oh, it is? Okay. V final cosine of 35, and this will be V final sine of 35. Okay, and then we're gonna add up our momentum. So we're gonna do momentum in the x and the y direction. Okay, so we'll say, let's start with the x direction. So momentum x direction initial is equal to momentum x direction final. So in the x direction, what's the initial momentum? Which thing's in the x direction? Which car?
Volkswagen.
Volkswagen. So you can say mass Volkswagen. Mass Volkswagen times velocity Volkswagen plus 0, right? Because there's nothing else going in the x direction. The Cadillac only in the x direction. Y direction. And then the final velocity is going to be the mass of both, so mass Volkswagen plus mass Cadillac, because they're stuck together, and that's going to be equal to V final cosine 35 degrees. Okay, but remember this is a vector, so that means we also have the y direction, so momentum initial y, like being very inconsistent with my notation, momentum y initial, momentum y final. In the initial direction we have mass Cadillac, velocity Cadillac, and then we have mass Volkswagen plus mass Cadillac, velocity final cosine 35 degrees. Okay. So the nice thing here is we have two equations and two unknowns, okay? And unknowns are the final velocity, but also the initial velocity of the Volkswagen, and we're only solving for the initial velocity of the Volkswagen. So we're gonna start by solving for V final over here, okay? So V final is gonna be equal to mass Cadillac velocity of the Cadillac over the total mass, cosine of 30, oh, sorry, that one should, one of these is signed. This one is signed. So that ends up being, Cadillac is 3 kilograms times 3 meters per second divided by 5 kilograms, which is the total mass sine of 35. And that's going to give us a final velocity of 3.14 meters per second, or pi meters per second, okay? So this is our V final. We plug that back in over here to solve for the Volkswagen. So that's this. That would be total mass over mass of the Volkswagen, V final cosine 35. So that's going to be 5 over 2, 3.14 meters per second cosine 35. And that should give us 6.43 meters per second in the x direction, if you want to be specific. Okay, so you just break down your velocity vectors into x and y, and you solve everything in the x direction and everything in the y direction.